Howdy! In this video, we're going to look at some basic properties of logs and inverse properties of logs. All right, so we have some cancellation properties here that can kind of simplify your life a little bit when calculating logarithms. So the log base b of b, what is that? Well, it turns out that equals to 1. The reason why is because when we convert this logarithmic equation into its alternate, which would in this case be exponential form, right? We start with this little b at the bottom, that b, to the power of the number on the other side, which is the 1. I'm going to color coordinate this thing, right? Equals to that b right there. Okay, which we know to be a true statement. So I'm doing b to the power of 1 equals to b right there. That's what I just did when I converted it into its exponential form. So for example, you might have, let's say you're doing common log, and so it doesn't actually show a log base. What if it just says log of 10? Well, then you assume that it's a common log and that the base is 10. So that would be 1 because 10 to the power of 1 is equal to 10. Okay. Next little property is log base b of 1. Doesn't matter what the b is. The b could be any valid base. B, or you ask yourself, this little b to what power equals to 1? Well, anything to the 0 power is equal to 1, right? So the little b right there to the power of 0, anything to the 0 is 1, except for 0 to the 0, that is indeterminate, which is something you will learn about in calculus. Right? Okay, so for example, let's say maybe you're doing, who knows, log base 2. It doesn't really matter. Any base, log base 2 of 1 would be 0. Okay, so if you're taking the log of 1, it's 0. All right, here's the last two are inverse properties. B to the power of, now this is a little strange, right? The base is B to the power of log base b of m. All of that is the exponent, right? This does simplify. I'm going to tell you the answer, and then we're going to rewrite it from exponential form into logarithmic form. Okay, so what it simplifies to is m. And when I rewrite it, you'll see why, right? But this is actually exponential form. Yes, it has a log in it, but the log is just its own, it's inside the exponent. So when exponential form, to get it into logarithmic form, you start with the word log, then whatever is on the base, in this case that b with the blue underline, that becomes your base here, of what's on the other side, which is that red m, log with base b of that number is equal to the exponent. That's the definition of a log. It's how you solve for the exponent in an exponential equation. Well, the exponent there is that whole thing that I underlined in green. And clearly you can see when I write it that way, yes, log base b of m is equal to itself, log base b of m. Let's do an example. So maybe it looks like, oh, who knows, e to the natural log of 20. Well, natural log has base e, so this is equivalent to e to the log base e of 20, so that would simplify to just 20. And that says ln there if you can't read that, e to the ln. Okay. And the last inverse property is log base b of b to the power of r. You could think of this as you ask this b to what power, which would be r, equals b to the r. Well, b to the r is b to the r, right? And when we rewrite that logarithmic equation, that one is in log form because it has a big log, not just a tiny log in the exponent. That's an exponential equation there. This is a big log. So we start with that little subscript b to the power of what is on the other side, which is r, is equal to the thing you're taking the log of, which I underlined in green there, which is b to the r. And clearly b to the r does equal b to the r. Let's do an example of, who knows, it could be anything. It could be 5, log base 5 of 5 to the x would simplify to just that exponent of x. Okay, so now let's pause the video and try the following examples. Okay, there's a few, and then there's one more there at the end that we're going to do. Here we go. All right, so simplify these examples. Pause and try them on your own first. Ready? Log base 8 of 8 to the power of 6, the log base 8 and 8. In a way, cancel, you just get 6, right? And the reason why is because this 8 to the power of that 6 is equal to that 8 to the 6th. You can see that that does, in fact, check out. All right, 2 to the power of log base 2 of pi. The 2 to the power of log base 2 does cancel, and we just get pi. And again, that's this kind of weird one here, the third row. If you rewrite that exponential equation in logarithmic form, you can see that it's clearly a true statement. All right, natural log of EDA. Well, if you have natural log, you might want to write it out. ln really is a shorthand for log base e. So I'm rewriting this problem as log base e of e to the eighth. So you can see that the log base e of e, those are inverses, right? So they cancel. So we do just get 8. And if there is no base written, you would assume that the base is 10. So that's equivalent to 10 to the power of log base 10 of 4x. So that does simplify to just the thing you're taking the log of, which is 4x. Okay, continuing on with a little bit more practice here. We have log base zero point 0.4 of zero point 0.4 to the negative root 7. It doesn't really matter that exponent's negative. It still just simplifies to negative root 7. E to the natural log of 3, that is equivalent to e to the log base e of 3. So that does simplify to just 3. All right, now it's getting a little trickier. Log base 5 of square root of 125. Well, it's not a perfect square. We can't just take the square root of 125. That would be too easy, right? But there's a few things we could do. Excuse me. I think what I'm going to do is rewrite 125. Let's think about this. That's equal to 5 to what power, right? 125. Well, 5 times 5 is 25. 5 quarters is $1.25, right? So that's 5 cubed is 125. Okay, let's rewrite it like that. Let's rewrite it as log base 5 of the square root of 5 cubed. Well, we can almost use that cancellation property, but the square root's in the way. But we can rewrite a square root as a rational exponent. So we could rewrite that as log base 5 of 5 cubed to the 1/2 power. And then we could simplify that 5 cubed to the 1/2 power. We multiply the 3 and the 2 to get log base 5 of 5 to the 3/2 power. And if you were able to just jump straight from the problem to that, that's fine. You don't have to show all those little steps. But that does all cancel. The log base 5 and the 5 cancel. And so we do just get 3/2 in the end. All right, next on the right, we have natural log of 1 over e squared. Well, it does not look like any of those forms we had here, right? But we can expand and rewrite out log base e in place of natural log if you want to. And let's manipulate this fraction and write it as e to the negative 2. Because then you have base e, that cancels, and we just get that exponent of negative 2 by that property right there, last one, which is at the top of the screen. Okay, and last but not least, we have natural log of e to the kt. That's an applied type of problem that you'll see pretty frequently. The ln and the base e do cancel, and you do just get kt. All right, that's it for the basic and inverse logarithm properties.